Okay, my outstanding friends, as you know, or you may not know, but if you've been paying attention, you know that I have dipole electron flood theory, which says that everything there is made out of dipoles, 100%. And I also say that light can speed up and slow down, and I have witnessed this. We did this in our experiments, and I can show you these things. Einstein, I'm going to tell you right now, this is my statement, Einstein was the one that literally destroyed everything they're doing in physics because of his light speed being constant and the assumption that space is a vacuum. And they know now, and there's no question whatsoever, it's not a vacuum. They still calculate everything on the fact that space is a vacuum and light cannot slow down. It's absolutely ridiculous. Ridiculous beyond ridiculous, and it is all Einstein's fault, really. And I think they set him up to destroy physics in the hope that we could build a bomb and nobody else would be able to, because they were trying to follow Einstein's work. And trust me, you're never going to get anywhere following Einstein. And of course we did build a bomb and blew up Japan. And Einstein was the way that they fooled everybody else by saying, "Oh, this guy's so smart." He agreed. Everybody in the world peer-reviewed him. He's all peer-reviewed. Well, peer review means absolutely nothing. Peer review means that you will just agree to say what everybody else says so that you can keep your job. That's what peer review is all about. It has nothing to do with reality. So I'm going to show you reality right now, and it's going to destroy Einstein, and it has to. It's just absolutely ridiculous, and everybody knows this now, but they can't speak because they don't want to lose their career. Okay, my friends, before we get into the details, let's see what the assumptions are as far as the speed of light. Is the speed of light constant? You always heard that. The speed of light just travels the same speed no matter what. Well, that's only in a vacuum, all right? And I can agree if there was a complete vacuum, there was no particles whatsoever there, but you're never going to achieve that in the first place. But secondly, if that was the case, maybe that could be possible, that it would never slow down. But there is no vacuum in space, and this is quite well understood. I mean, even a 10-year-old can look out and see all the stuff that's in space. I mean, it's just not a vacuum. And I can show you there is a ton of fields out in space which are interrupting light flowing through it. So they say the speed of light changes in air and water, yes, because it's meeting with resistance. And it still meets with resistance in the vacuum of space, which is not a vacuum. So it says, is C, the speed of light in a vacuum, constant? Now, I can't disagree with that. I can't disagree with that, but I can't see a vacuum ever happen, certainly not in space. Absolutely not, no way in the world. Okay, my friends, before we get started, I am going to be showing you these two particles which we found. Now, this is Fermilab, and this is back in 2013, and the guy's name is Don Lincoln, and he is literally the voice of particle physics now. He's got videos coming out of your ears, and I would like to engage with him, and he has so far, you know, we talked, but he won't discuss things with me. And I have found these same two particles. Now this goes way back. We go back a long, long time ago. And we were taking pictures of these using CMOS telephone, just a little, you know, the Galaxy S3 phone. And it has CMOS in there. And they said, no, you can't use CMOS to see particles because it destroys, there's too high energy and it destroys the CMOS. However, we were using light. They were using huge particles, smashing the CMOS into little bits. Now they have upgraded. I went to the University of Geneva online, Switzerland, and I told them we were using CMOS. They said, no, you can't. And he said the same thing. You can't do that. You're all way off balance. And really, he was not nice to me at all. Geneva was very nice. And they listened, and guess what they ended up doing? They ended up doing CMOS detectors See, here's what we were using. We were using, this goes back to 2012. This is when we started. The Samsung uses this CMOS imaging sensor. Sony provided the camera functionality. Well, this goes back to 2012, and I said to him, I said, we're seeing these particles. And then eventually, they went and did an upgrade. This is in 2019. CMOS detector system development, CMOS, for LHC detector upgrades. A big upgrade. But I'm telling you, it's very, very expensive. And see, here's exactly what they did. They hardened it. Where's there something? See? Integration of novel, radiation-hard monolithic CMOS. They couldn't use it before because they were the particles. We're using particles this big. That's the particles we're using. CMOS is designed to see these particles. I don't care how much energy is behind them. But you can't hit them with this and expect that CMOS to survive. And that's what they're using, because they're using huge particles like this. We never get any bigger than this. That's this. This is all we ever get to. So they went ahead and upgraded. But listen to this. It's going to be like 2029 or something before they... Look at this. This is for their high luminosity, expected to be operational in 2029. And they did focusing, and they did this upgrade, and they're supposed to see a factor of increase of 10. Now, we're seeing things that we can't, we have so many collisions, it's absolutely impossible to count them. They're going from, they wanted to increase the luminosity, means increasing the number of collisions. So when the particles collide, they're coming head on. Well, you can almost never hit them head on. They get billions of them, and literally, I'm not kidding you, billions. And they're hoping for 140 collisions, and that's the upgrade. Each time two particle bunches meet in the center of the, they come around, backwards and so forth, and boom. And some of them will hit head on, but most of them just bounce off the fields, 99.9999999%. But out of billions and billions of them, they're hoping for 140. They're only getting 30 collisions right now. Every single one of ours is colliding, and we use it because our fields are not hitting head on. They're coming sideways and cannot get out. They got to go in, and they got to smash. Ours is twice as effective and thousands of times more efficient. Okay, what I want to explain to you is this was literally just an accident. And a guy in Australia, Rod Warren, was playing around with a laser. And he just got a new phone, which this goes back to like 2012. And it was this same phone here, Samsung Galaxy S3. And he used the selfie side as he was doing the double slit experiment. He only used one slit. And instead of making a flat plate, he used round finishing nails, literally finishing nails, real tight, close to each other, made a little tiny slit, and then when he shot the laser through, it came out here, that white, incredible radiation. You see what's happening? It's pinching this down, and as it comes out, it's pinched, and then it goes back to being normal. This is how a venturi works. It's not unknown. It's completely understood. It's an accelerator, and it's an accelerator. Now, light is literally almost like a fluid. And as it flows through the air like squirting water, when it hits this venturi, it's got to crush itself. And when it crushes itself, it does better than at CERN. What they did was to get this explosion of particles to split and go crazy, was they hit head on. Well, when they hit head on, there's a tiny little particle way deep in the side, and there's a field all around it. It's like a balloon around a particle way inside. When these hit, they just bounce, the balloons bounce off each other. So eventually, though, every now and then you get one, it'll go all the way smashed so solid that there's no bounce like this way, but that very almost unheard of rare. Billions of particles go back this way and that way, and every now and then one or, like they said, they want trying to get up to 130 something like that. It's insane. We get every single one of them, the field crushes. Now, not only that, if it was just the electron particles, that would be one thing. But we also have another perfect situation. With these white particles that can squish down and get through is the black particles, which cannot. The black particles hit and they just go bang, 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 and they bounce off. So they end up squirting the white through and really giving you a major spray. But this is what a venturi does. It's as simple as that. And what Rod did, who was the guy that was doing his original experiments, I did some too, we had some other guys doing it, and everybody got the same result. He used the selfie side from here and from there and from here and from all over the place. And this goes back 10 years. And that's the venturi, and that's exactly the effect. You see it going flat like that? That's where the energy is. This is where all the luminosity is, and then it comes back out and it flattens back out, or it balls back up again, and it turns back into normal particles. Okay, my good friends, before I get started into this, I just want you to know I am going to be talking almost exclusively about Fermilab, because they're the ones that are presenting all their evidence to the world. And their presenter is Don Lincoln. He is Fermilab's spokesman. And this is his particles that they found way back in 2013. And he's explaining this fixed particle and this point particle. And again, this is Don Lincoln, and his conclusion is that the fixed particle always is the same size, never changes, but it can have a fuzzy edge around it. The point particles are mathematical abstractions, zero size, but they have an extended field. I agree with both of those statements. Now, he also says there's a quantum foam. This is, again, Don Lincoln, and he's Fermilab's spokesman, same basic time frame. He's saying that empty space isn't empty, and that's, I agree. And the way he explains it here, which is nicely done, is that it's like the head of a root beer. There are bubbles going on and off all the time, flashing on, going off. Well, that's what's happening in space. When you look out, there's a glow. And that glow is when different particles bang into each other just for an instant, and then they go on their way. Space is not a complete vacuum by any measure whatsoever. There is a ton of stuff out there, and it's continuously banging into each other. And there is huge fields surrounding all kind of planets and anything that's out there that's got a spinning nature to it. It creates a field surrounding it, and they're all dipoles. Dipoles are created when things spin. All right, remember I just said spin creates dipoles? Well, here it is right here. An electron can have two types of spins. Each one of these spins creates its own intrinsic spin magnetic dipole moment with its own orientation in space. That is basically true. Now, this is not all new for me. Trust me. This is 1970. Right after I got out of the Army, I was in Nike Hercules missiles, and I went deep into, as deep as you can get, into physics and chemistry and everything there was to do with particles. And I came up with the conclusion that all there was dipoles. It's two types of interaction, dipole interaction. There is no such thing. Everything was a dipole. You cannot have, well, anyway, I'll go into those deeper. But anyway, the transfer of energy is from light to atomic vapor. Light is literally atomic vapor. And it ends up building things like plants grow because they get light. Light is actually mass. It has mass to it. And it is particles. And when they hit things, they have a weight to them. And I know this for a fact because if something is heavy, if something is hot, it will weigh more than if it was cold. I know you think, oh, no, when they're hot, they rise up. No, that's only gases. If you increase the volume due to the heat, yes, it will rise. If you don't increase the volume, it stays the same size, but it gets hotter, it gets heavier. And the reason is because it gets invaded with particles that have a weight. They have a weight. And it's very, very tiny. But they do have a weight when these particles invade and they warm something up. But listen to this. The particles you use to run your car and your electronic devices and all that, they have no weight whatsoever. No weight whatsoever. You charge your car up and it weighs 4,000 pounds, and you drive 500 miles and you have no battery left, it still weighs 4,000 pounds. You charge it back up again, it still weighs 4,000 pounds. All you're doing is forcing the white particles that have no mass whatsoever, which is what Don Lincoln shows, and he agrees to it. He says they're like a mathematical abstraction. Now, we can actually see these in our experiments, so I'm showing it to you. But don't forget now, the spin is created, or the dipole is created by the spin. So if it doesn't spin, there's no dipole. All right, this actually proves a ton of things in one little picture here. Now, this was taken by Rod Warren's nephew, Dylan Carpenter, in New Zealand. And he just sent me a couple of pictures, and that's all. That I've never heard another word from him. I try to contact him. And Dylan, if you see this, please contact me, my friend, because you did some fabulous work here. You need to be recognized as, discovering this. Basically, this was a discovery. He just got a new cell phone. He went on, click, 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 take a couple of pictures, apparently at night. I don't know anything about this other than the pictures. I get all kinds of stuff sent to me, and really, they're like mysteries I have to try to figure out. I like it. I mean, I enjoy it. But this shows the dipoles. Every dipole has a field around it. You see the fields? And this, I'm going to tell you right now, every one of those is spinning, and I can tell you why I know that. You see these? These are all dipoles. They all have fields. Fields. They all have fields around them. Fields around everywhere. Everyone is a dipole. A lot of people don't understand what these gigantic particle accelerators like Fermilab and CERN and the other ones, Lawrence Livermore and so forth. Why are they doing this research, spending these billions and billions of dollars? What are they trying to find? Well, here's exactly what they're trying to find. All right, they're looking for the smallest particles that make up the universe, the building blocks of the universe. What are we made of? What's everything made of? How did the universe begin? Good question. What secrets do the smallest particles, most elemental particles of matter hold? What are these secrets? What is it that they have not been able to unlock? And how can they help us understand the intricacies of space and time? It's exactly what I am trying to explain and to discover myself. Now again, this is not new to me whatsoever. I've been doing this my whole life, and I came up with the dipole electron flood theory, which is that electrons are not made of just a negative. They are a dipole, little tiny one, and 1,823 of those make up what they call a proton. And what it actually looks like is like this instead of like that. All right, well, look at this. That's a proton, and that's a neutron. All right, they're almost exactly identical weight, except one extra electron. And the reason is this is not balanced. It's 1823, the proton, which means it's charged, because it's not even numbered. This is 1824, which is almost identical, same weight, and it's neutral. And the reason it's neutral is because it doesn't want to take on another electron or give one up. This one is in between taking one on or giving one up. That's because it's a proton. All right, and all that is one of these is a proton, and it wants one more, or it wants to shoot one off because another guy wants it more than this guy. All right, and that's what the actual proton is. So when you get down to light, here's where you are. This is where we started with here. They start with this. This damages things. It causes a lot of injuries. You can really, really hurt somebody when you break this up, and a chunk like this smashes into something. A whole different story than what we do with this. You can't hurt anybody with this. It's just light. All right, this is mass. This is big. These are like bullets. These are like 50 caliber, and we're shooting like virtually nothing. We're just like wind. All right, so this is the difference here. And what can we understand about our universe? And what can we understand about maybe even getting some free energy? Who knows? But I have to refer to Fermilab because they're the only ones that are really touting everything that they're doing. And it's Don Lincoln is the guy. And I worked with him years and years ago. I didn't really work with him. When I say work with somebody, I mean I interacted with him. And, you know, he sort of discounted my work. So I went on my way. And he still discounts my work. But I'm going to show you that I don't know why. I have no idea why he won't look at it. I mean, this is a government agency. They're supposed to be doing work for us. And he's always asking, does anybody have any questions? Can I explain something? And he's on virtually every day putting on another video about, you know, reinforcing the model that they have now, which is not correct. So let me make my case against their case. But again, this goes back a very long time for me. And the only reason I can make the case now is because of Rod Warren's experiment that showed that light can accelerate, light can slow down, light is a particle, it consists of two back-to-back Dirac neutrinos. And you can see them with CMOS, and nobody ever knew this, and it was not accepted because we did something different than everybody else did, just different. So when you're different, you're different. It doesn't work out too good usually when you're different. Okay, my friends, a little interruption there, and I believe where I left off was about Fermilab. Now, and I think I showed you a few other things, but let me be sure we understand each other. This is Don Lincoln again, and again, I am going to refer to him just basically as the other side to this equation. I have my opinion and my evidence, and he has his evidence and their opinions. But I have found these particles. I mean, there's almost no question whatsoever because we started with light and we found these particles. Now, he also talks about the standard model and he talks about the quantum foam. All right, the standard model is this right here. And there's all kinds of little quarks and leptons and forces and this and that. And it's the most successful theory ever. Well, that's not true either. It doesn't work. So I disagree with that. I agree with these particles and what he says about them, that this is all the weight and it can't change size, but it has a glowy edge. And this has no mass to it to speak of, but it has a huge energetic field. No question whatsoever, I agree with that. Quantum foam, I agree with him 100%. Empty space is not empty. And he says it right here. He says the quantum foam is real. The microcosm is in continual motion. All of these little particles are interacting. The universe is not only stranger than we imagine, it's stranger than we can imagine. Again, Don Lincoln. He is the voice of particle physics now. As far as I'm concerned, he's the guy working with Fermilab. He represents Fermilab. He's their spokesman, senior scientist. And I am going to present my evidence, and I believe that it's incumbent on somebody, certainly a government agency, to discuss what I am presenting in a reasonable scientific manner. That's all I'm asking for. All right, so let me show my science. We can see their science, and these doing this gluon. I mean the muon experiments. Anyway, I don't know. G is of the muons, and I'm going to show you the muons. The experiment aims to measure the gyromagnetic rate. You know. Anyway, they're doing all kinds of stuff. And again, this will be Don Lincoln. Nope, it's not. It's not Don Lincoln. That's amazing. Anyway, they're trying to find out the physics is yet hidden from us. All right, so again, Fermilab, they're the big ones that are talking about this day after day after day. This goes a little bit before Don Lincoln. This is 2011. He's the first I ran into him was 2013 when I saw his particles and we had the same particles. And I got a hold of Don. I said, we found your particles, and I sent him all our stuff. And he didn't think that I was on the right track, so he dismissed it and didn't want to interact and asked me not to bother him, you know, basically. All right, so here's the one that shows everything in a nutshell. All of these fields, if you send particles through those fields, they are going to push back against the field that's coming at them. That's how field-to-field interaction works. It's called a Casimir effect. They just bounce and they slow down each other. Now, spinning particles create fields. You see all the dipoles I talked about? The moon's not a spinner. It doesn't spin. That's the moon. No field. No fields around it. This field is from somewhere else behind it, from some big thing. I don't know. Boy, there's some really messy looking things going on out there too, which I am having a very hard time understanding. But I do understand this. They talk about the redshift. They say that the universe is expanding and pulling light. In other words, this is really what's happening. Light is spinning. But if you looked at it from the side, it looks like a wave. And the real long waves are red. Bar here is green. Right here is really blue. It's really crushed, really heavy duty. So what happens? They say the universe is pulling away. I say no, light is just slowing down. It started out at let's say it started out blue like this. By the time it hits us, it's down in the red shift. Yes, I agree with that 100%. It is red shifted because it's pulling away. Well, what if we were crushing into it? It would blue shift. And that's exactly what's happening. That's a blue shift. And that's because the moon is going this direction and the light is coming this direction and it's crushing it into the blue range. So it came in at whatever it came in at, and it's being crushed down to this blue range. And as the moon is going this way, this is being pulled away, and you're getting more into the red range here. So this shows that this shows that a non-spinning mass, as the size of the moon, has no field. All of these, every single one of them has a field when they glow and they have a dipole reaction to the spin. And this is where our global warming, a lot of it is coming from, is that the outer zone of our atmosphere is crushing in all the other particles in space, and it's scrubbing away out there. It's because we're not in a vacuum. We're scrubbing through particles like in a soup, but they're a soup of magnetic, interacting, energetic particles. When they hit, they start to create a little bit of heat. And out there, way out on our atmosphere edges, it's 2,700 degrees or something. You see this? I drew this a long time ago, just to show light coming from the sun. The surface of the sun is 10,000 degrees. Way out here, it's millions of degrees. For the same reason we have it on here on Earth. It's because out here is filled with all these particles. And this is scrubbing through it, spinning and being ripped through the arm of the Milky Way, and has to get through all these particles, heating its outer atmosphere to millions, where it's only 10,000 on the surface. And they have no explanation for that. And the only explanation is because it is scrubbing. We have the same thing here. It's 100 or so on the surface, and way out here at the outer edge where our ionosphere is, it's thousands of degrees. There's no explanation for that either. And the reason is because we're spinning through the particles that are everywhere in space. No matter where they're coming from, if it's a particle and it's a light particle, it has a field and we have to scrub through it. The moon radiates. It does not emit. It's a radiator of the bounced energy. The energy bounces back. That's why it's a dim light. It doesn't emit light. The sun emits light. All right, and the Earth does a little of both. All right, so that's basically what we're looking at. You see this? That's a dipole. There's the black one, there's the white one. And they're showing it gearing up to search for gravity waves. The gravity waves are just what I showed you. Those are the magnetic fields. And particles passing through this stuff, there's no way in the world they don't slow down. Everything that they've based physics on is wrong because of Einstein's constant, and they're saying that the space is a vacuum. It's clearly not a vacuum. And even the Fermilab, he just says it right here. He says it's quantum foam is real. And it has consequences. Everything that has to pass through it is bouncing through it and it's slowing it down. That means that the universe is not expanding necessarily, stretching the light, which is why they say we have the redshift, because, well, light can't slow down, so the only way it can shift red is if you pull it away. No, it can slow down. Okay, once again, Fermilab, and this again is Don Lincoln, and he's talking about neutrinos, which basically are the smallest particles that they know of. And this is the Dirac and the Majorna. It's just, I'll explain that later. Now, the neutrino is one of the most mysterious particles in the Standard Model. The original idea of neutrinos formulated in response to a problem in beta decay, in which neutron converts into an electron and a proton. As I said before, all it is one extra electron attached to a proton makes a neutron. So this is not, there's no mystery here. That's just what's going to happen. An electron and a proton is a neutron. So there's no discrepancy here. Now, he's talking about the smallest particles that exist. All right, so don't forget, this is their mission, is to find the smallest particles that exist. And this is basically what they found, is the smallest particles they can find. And we found them too, but we found them in the light experiments. And here they are right here. This is the Fermilab particles I just showed you, and here's the ones we found. And we started with light, so we didn't start with huge, big masses of things. We started with the smallest particles, basically a photon. So as you remember, Don Lincoln's point particle is this black one with the glowy edge. And the glowy edge just is whatever color it is, red, blue, green, so forth. And there it is right there. It's virtually identical. I mean, completely identical. And don't forget, he said this is the only one that can get puffy and it just almost doesn't exist, but it has a big magnetic field around it. And I agree with that, because this has no mass at all that I can determine. I mean, almost zero, but boy is it energetic. And this one is behind the black particle, so it's not charged. This one's charging up as it impacts, and then it will flip, and this one will go in the front. That's the upspin and downspin, and this is what the particle looks like, just black and white. Now, when we hit the venturi, the whole thing exploded. So the particle was just going in its normal wave, because it's a particle with a big field around it. So it creates a wave as it goes. I think I have some shots of that. Hold on. Yeah, here it is right here. This is normally what a pulsed red laser is. It's a pulse of light. And each one of these is particles. Now, this is the leading tip. It picked up instantly as it was pulsing. And it's getting ready to accelerate to go into the venturi. And at this point, there's a particle in there, but you don't see the particle. You see the wave. And why would you see the wave? Well, because the particle is way inside and it has a big magnetic field. And all of these have magnetic fields. Every particle in the air has magnetic fields because it's made out of particles that have magnetic fields. So these have to push them out of the way, like a soup. And as it does, it gets glow, a lot of glow, and these get a little bit of glow. All right, so there's the wave particle nature. Now, after that, we accelerated it. And it is a very simple process of going through the venturi. And this is the venturi here, which I don't know if I explained it or not, but it's two cylinders, one on each side. And they're very, very close together, so only the white can get through. That's the particle actually accelerating, because that's what a venturi does. It accelerates things. And at the same time, it forced the fields to crush together here, and only letting the white come through the venturi, keeping the black smacking it, boom, 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 because it's got some heft to it. And here I can show you that it does push the white. Here it is pushing the white. You see it? See the black? This venturi was tuned to a point where it would let some of the black come through in addition to the white. And the black is literally forcing the white ahead of it. It's pushing it. So the black can push the white. Of that, there appears to be no question. All right, so let's look around at a couple things. I showed you the light can accelerate and it explodes at the venturi. I showed you the black portion of the Dirac neutrino. These are neutrinos, the smallest particles that exist, and they are part of light. I agree. And not only that, you could separate the black from the white, which is exactly what we did. We separated the black from the white. And the black can push the white, of that there is no question. This is the light creating a wave surrounding the particle, of that is pretty obvious. This is the acceleration phase, so light can accelerate, that's quite obvious. And that is the particle inside the wave. Now what would that particle look like if you could actually see the actual particle? Well, guess what? We can see it. And I will show you that right now. This is what they look like as they're coming through the air. All right, let me turn this light off. All right, sometimes that helps a little bit, sometimes it doesn't. Now, what are we going to see here? We're seeing the light coming in. And the only reason we're even be able to see this is because it's going to smack into this venturi very shortly. All right, up here you can't see any particles at all. There's a ton of light coming through here. You don't see it. You could never see this until it starts to gain energy prior to actually colliding. These wouldn't have any energy basically to see until they collided with something. The only reason we can see them up here is because of this radiation that's coming backwards. And they're actually glowing inside the air where they normally wouldn't glow real glowy like this until they actually collided with something. And then you see the bounce back as a color. Here we're actually seeing it show up in the middle of the air. That's very unusual. And the only reason we're seeing these so perfectly is because they're directly in line with the venturi. The ones that aren't in line with the venturi, you wouldn't ever see them at all, except that they're being pushed back at. And I can show you that. The backwards radiation is absolutely stunning. They call that the reverse EMF, electromagnetic forces. Okay, just think about this. Just give it a little bit of thought. I showed you the single light wave coming through. All right, and it creates a wave. I mean a field, a wave, and it's a particle. And the field is the wave. All right, it's a magnetic field surrounding the particle, and that field has to push into everybody else's field, so it looks like a wave coming through. Now, back here, there's very little energy until it starts to accelerate, and now it's gaining its own energy going forward so we can see it, and the particle is becoming extremely brilliant, and here it explodes and the black divides from the white, and only the white is allowed through the venturi. Look at what you're seeing here. This is extreme luminosity, extreme. That is glow on top of glow. Now, why are we seeing these little things here? What the heck is going on with that? I can tell you what's going on with that. These are in the air just as this one is. They're all over here. They're all coming forward, a whole batch of them. You never would see them, ever. Just like I told you before, they would never, ever show up. The only reason they're showing up is because there's so much energetic activity going here. And the reason they're showing up here is the tips of them. Just like the tip of this is becoming so excited because of the radiation going backwards. You see this backwards radiation field here? This is what's called reverse EMF. You see that? This is an explosion from the impact at the venturi, and that's just incredible amount of illumination. And again, you wouldn't even see these fields. They're coming forward, but you never see them until this bangs back at it. All right, this one is glowing itself because it's being sucked forward. So when they will glow if they're being accelerated or pushed back against, which is the same thing, as acceleration is pushing hard against something else, and pushing back at it is the same thing as pushing hard forward. It's one way or the other. And these are being pushed back in so much extreme energy that it's just brilliant, absolutely brilliant. That indicates extremely high energy. So we went from almost no energy up to extremely high energy, so radiant that it just exploded everything here. If we could tap into this right here, right after the venturi, and make the venturi very efficient so that all of these particles, we would harvest them. A big venturi, bringing all of those fields down together, and the right frequency on a pulsation, the right intensity of light, you know, probably on the upper end of the blue spectrum. And coming out of here, you need something that will collect all the different frequencies of light. They call them, I believe it's called perovskites. And all they are is different transition metals, a thin film of different transition metals, which means they will absorb different frequencies of energy. Because when it comes through here, this brilliant white, that's all the frequencies, basically. As far as I'm concerned, that's every frequency. So you need to have something that will absorb basically every frequency. And or as many as you can. As much of this as you can harvest, the better. And this white is the stuff that goes into your battery. This is all separated out automatically. Normally you have to do a lot of mechanical work to break the white away from to break the white away from the black. Here it just happens automatically. And it squirts right onto whatever we can focus this all day long, never have to shut it off. Very cheap. Just a cheap laser and something to absorb and just a little mechanical venturi. And if that works, which it should, this energy is extremely more than this energy. That means you have a net gain. That means free energy. All right, I hope I've shown enough to convince you that we have discovered these particles using light, not protons. And we were able to see them using CMOS because we were using light and not protons, so we didn't damage the CMOS. And again, this goes back quite a number of years. And I think it's time we look at this because the Earth is in trouble. It's in trouble. Now, it sounds spectacular. I agree. That's just what it is. It's just happened. And it's just accident. I knew about the dipole flood theory forever, but I could never prove it until I saw this. And it just popped up one day online. I got a hold of Rod Warren, and he worked with me for quite a few years. And we tried all kinds of different things. I did the same things here, but he was so good at it. It was just incredible. And here's what the bottom line is: we can separate the muon neutrino, which is the muon, turn it into a sterile muon from the neutrino phase, which attaches to the electron neutrino. The muon neutrino, electron neutrino are together as a unit. That's what's called a gluon. Now, when they hit heavy water or whatever and create Cherenkov radiation, which is another medium from where they were coming from, we created our own medium at the venturi. So at that point, the electron neutrino left in as a shower, a focusable shower. We can focus this right onto a receiving panel, and the black can get through. But if you don't harvest it, it just attaches to the black right away, because they can't exist on their own. The white away from the black, normally you won't ever find that. They will be attached together. All right, the only way you can do it is if we did this with the venturi, or if you do it with the gigantic particle accelerators, and then you'll have the separation happen. I mean, I'm sure it happens every now and then in another way. And it also, I believe, does happen using chemistry and enzymes and so forth. You don't see it as light like this, but it's the breaking down of these black and white particles to recreate something. Chemistry is very, very interesting, extremely interesting, because it's nothing more than these particles being turned into different globs using different ways of doing it, heat and salts and acids and enzymes particularly. Enzymes are the key. Those things, baby, they are powerful, and they just tear molecules to pieces and rebuild them instantaneously. I mean, millions in less than a second. So we got a little work to do, but I think that, you know, if we take a good look at what I'm showing here, it does appear that it's exactly identical to what they have found at the major particle accelerators. Only we started with light, so we're honestly, it's a couple steps ahead here. This is what they're looking for. This is their total mission in life, is to find the tiniest particles that exist. We actually broke these apart, the black and the white, separated them right there. So, and another thing, this is fission and fusion. This is fission right here, breaking the black away from the white. It's fission. Coming back together, it's fusion. I don't see any other way to look at it. All right, and if we can do this, and you just harvest that white and push it into your batteries from a device like this. Hold on one second. This is what we should be trying. At least give it a shot. We can see, this is no question, this has happened. We separated the white from the black. The white is all you're going to use to run your car, your house, your ovens, your lights. Everything is only the white does the job. The black, you don't want to push into your car. Again, if your car weighs 4,000 pounds and then you drive 500 miles, it still weighs 4,000 pounds. If you fill up your batteries again all the way to the top, still weighs 4,000 pounds. And they had a guy actually do this with the electric vehicle to show that that's the fact. And it was exactly the same weight. Exactly. It didn't add any weight. Now, gasoline, if you put gasoline in your car, every gallon, I believe, is 6 pounds. So if you put 10 gallons of gas in your car, that's 60 pounds. 60. This is zero weight, no weight whatsoever. So the only thing I can say is all you're pushing into your car is the white, and that's the only thing that comes through the venturi if you tune it correctly. So you can just drop that right down into your battery through a photodiode. It goes through and it can't come back. A diode is a one-way device. You push it down, and this just slap it too. Squirt, 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 squirt. Just like a syringe. Down it goes into your battery, and then your battery's all filled up. You go drive away. Or you don't even have to. You could just plug this thing into your car and drive down the road. No batteries at all, basically, as far as I'm concerned. You know, you certainly want to have something to back you up, but you can maybe even have 2 or 3 in the car, so if one goes bad, the other one kicks in. These are going to be so cheap. You know, if it works, and I don't see any reason it shouldn't, because that's all a solar panel's doing. It sits here, and the sunlight hits it, and it drives electrons down into conduction, down into a battery. Same thing. All right, you see this? This will be Don Lincoln again, talking about the smallest particles in the universe. What about the largest? Now, the smallest weighs way less than an electron. Well, that's because they don't understand the electron is made of both the black and white particle. An electron is not just a glowy little burny particle. It also is, literally the muon and the electron neutrino, the two of them together, which is a dirac. Now he claims it weighs, well, I'll show you what he claims. Okay, so don't forget now, they're looking for the smallest particle that exists and the mass and all of the characteristics of it. And these are going to be Don Lincoln's comments about this, and I will make my comments. Now, he's saying in terms of mass, the questions are relatively simple to answer. The lowest non-zero mass particle we know of is the neutrino. Well, there's 2 different flavors of neutrino, which is the muon neutrino and the electron neutrino. And the mass is literally all in the muon neutrino. The electron neutrino has virtually no mass whatsoever, but it is the energetic particle. So now, He's saying that the lowest non-zero mass we know of is a neutrino, Lincoln said. He pointed out, however, that we don't have the exact measurement of a neutrino's mass because the instruments used to calculate mass of fundamental particles aren't sensitive enough. Well, I think I can calculate its mass, and just by using mathematics to say how much does a electron weigh. All right, and then we can divide a proton by the number of electrons. We'll work this out in a minute. Now, he says a neutrino is a particle, sort of the ghost of the subatomic world, Lincoln said. Neutrinos interact very weakly with matter and are the second most abundant particle after photons. They behave more like waves than actual particles. In fact, there are trillions of neutrinos passing through you at this very second. Neutrinos weigh nearly nothing and travel close to the speed of light. Well, let's take these statements one right after another. A neutrino is a particle. I agree. Sort of the ghost of the subatomic world. You could look at it that way. Neutrinos interact very weakly with matter. No, they interact very strongly with matter. They are part of matter. And they are the second most abundant particle after photons. Well, the neutrinos make up the photons. So they're just the same thing. Now, they behave more like waves than actual particles. It's the field surrounding the electron neutrino that acts like a wave, yes. But the particle part is the black, so they have a particle and a wave. The neutrino, or the electron neutrino, creates the glow, and it makes everything else glow because it's a field. And the black part just pushes. In fact, there are trillions of neutrinos passing through you at this very second. Absolutely not. Those neutrinos are nothing more than light, and they're bouncing off of you. They're not passing through. If they were, they would be in the extreme high energy range, which would kill you. They would be the high energetic particles, the dark particles, gamma rays and X-rays and so forth. Now, and those will damage you because they're just the black part. The white part is gone. All right, so there's no bounce factor. Now, so you're saying there's trillions passing through you. That's not true. Neutrinos weigh nearly nothing and travel close to the speed of light. They are light, so they're going as fast as the light is going. And the light doesn't always go the same speed. It can go fast, it can go slow. I've shown this a million times. There's the light going, speeding up. That's not going the same speed. That is speeding up. All right, and here it is, the black pushing the white, as I showed you before, coming through the venturi. The black just pushes the white in front of it. So the black has no energetic value to it. It's just a carrier or a pusher. And in this case, and light is bound to it. The light part is bound to the black part. But the white part, as you can see, goes like this. The black part just keeps going with the way it goes. It just never gets bigger, never gets smaller. It's a fixed particle. Exactly like they said at Fermilab. And I agree with that 100%. So this is light not accelerating. That's just not accelerated yet. It's just beginning to accelerate. And this is light fully accelerated. So we know that it can accelerate. Einstein's wrong. If there's fields in space, it has to break through those fields. It's going to slow down coming to us. So here's the blue actually slowing down. You see it coming in real hot and fast. And there it is. You can see the two particles only way out here. But blue is very, very fast. Now, I think I showed you this before, or I will now. This is, when they look at light, they see a wave. And they think it's just flapping like this, like a straight line particle. No, the particle is spinning like this. All right, just as you see here, this is spinning. The particle is drifting to the left, spinning to the right. This is one shot of the same particle all at the same time. And it's here, it's really fast. And then it just starts to slow down. Same thing as the redshift coming at us. Light coming from outer space is not, the planets and everything else is not being pulled away to make the light look red to us. It's coming at us and just slowing down as it comes to us, because it has to push through all these other fields in front. So as it comes forward, it's in a blue range. It starts hitting things. Boom, 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 boom. And eventually it becomes the cosmic microwave background, which means it's just not moving. It's just laying around out there. And these particles are just like a soup, because they've used up all their energy by banging into everybody else's field. So that accounts for the cosmic microwave background. It's just out there. Okay, here's where we differ substantially. This is Don Lincoln again. He says an atomic nucleus is made up of neutrons, protons, and electrons. That's the standard model. Now the protons and neutrons themselves are about 1/10 the size of the nucleus as a whole. So the nucleus is the core, and they say that protons and neutrons are about 1/10 the size of the nucleus as a whole, Lincoln said. An electron has near zero mass. Well, that's the white part, and I agree with that. But it actually weighs 500,000 times more than a neutrino. Where he's coming up with this, I don't know. Again, whose exact measurement is impossible to make at this point. I mean, it's impossible what he's saying. Well, it could be, but I'm just saying it's impossible to say it with any authority. So, and the electron has near zero mass. I agree with that. There is no weight to it to speak of, but there's a lot of burn. And then he says it actually weighs 500,000 times more than a neutrino. Well, it is a neutrino. It's an electron neutrino. That's all it is. And it turns into an electron shower when it is accelerated like we did. So this is all impossible to understand. And here's what they say. Here's matter. I agree with that. There's all kinds of things together. And molecules are made of all that kind of stuff. And there's little bits and pieces you can call atoms, yes. And these are the atoms in the periodic chart. And then they have a nucleus inside. Now he's saying the nucleus and the electron are completely different. That these are protons and neutrons, like two monstrous things like this. All right, and they all glue together to make the nucleus of an atom. The electron is just a tiny, 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 so tiny it's just, it almost doesn't exist, and they don't even count them, to be honest with you, in the weight. And I can agree with that. They don't have any weight. So now, then he says, out of this, you have protons and you have neutrons. So the black and the red. All right, out of the proton, you get all this stuff. And you have gluons and quarks and down quarks and strings and so forth. Now, I say that the only two things that make up anything are the muon and electron neutrino. Everything is made of those. There's only two things. And you can call them strings if you want, but what they are is what I showed you they are, is a black and white particle. And from there, come this way, and yes, everything else goes this way from the black and white particle. You don't go from here to there, you go from here up to here. You see, this is what they call a particle zoo. They have all these different top and charm and up and bottom and strange and down and electron, muon, tau, and tau neutrino, muon, neutrino, electron, neutrino. Well, the only ones that really exist is the muon neutrino and electron neutrino, and they're normally fused together. That's the black and white particle. So don't forget, my claim is that every one of these is a muon neutrino and an electron neutrino together. And a big ball of them, which is 1823, makes a proton. 1824 is an even number, so it's not charged. It doesn't want to give one out or take one in. At 1824, it's a neutron. So that's the only difference now. And they're showing all these different things, and it's because of the type of collisions they do. Or they see all these debris, literally debris. We see the actual particles that were light, started with light, and actually divided and came back to being light, or particles again. All right, let me just go back over some of my claims. This is the way light comes through. It spins just like this. All right, this is the slit. And you can see it literally is the pattern of a drill bit. You see it? Just take your time and look at it. Now, why are we seeing these little lumps looking things and all these little lines? It's because the light, as it spins through here, goes either to the right or goes to the left. And because this has a field and every other particle has a field, they set up, they're so concentrated that they set up these exact patterns, exact lines, is because of the concentration of them. And I will show you when you want to see concentration. I'll show you some concentration. This is coming through the slit, and these are the concentrated white particles that say, you stay away from me, I'll stay away from you, and they set up these exact lines. I mean exact. Now, right in this area, they are so confined that they're just exact patterns. You see them as little, they call them interference patterns. They think this is a flappy wave. Well, this is not. This is a spinning particle. Some spin off this way, some spin over the top and come this way, back and whatever. But most of them get crushed together, and now their fields are just crushed. And all you have is white. The black stays on this side. That is, as far as I'm concerned, that is generation of electricity. It came through hardly hot at all, and then it just get this. That's just enormous increase in energy, enormous. All right, here's what happens at CERN and Fermilab and all of them that are using protons and neutrons. They're going back and forth, and then they slam here. And they only get a certain number, very, very, very few, out of billions, and I'm serious, billions and billions of particles. They ended up with like 100 hits or 130 hits or something like that. Because they have to hit exactly head on. Normally they bounce, they're like rubber balloons because they have these big fluffy fields, and they don't want to hit head on. They will never ever do that. Very, very rare that they hit head on. That's why there's only just a handful out of them, out of billions and billions. And so, but when they do hit, they see this. And what is that? It is all those particles inside, which is nothing more than these things here hitting head on, and every bit of them just going flying. And the real tight ones that were really tight on the inside, when they go, they take off forever. The blue ones, they never come back. They were so tightly held. When they go, they're gone. The red ones were way out on the outside already, so they just sort of bounce around and they come back. And that's what they call their Higgs fields. Now that's obviously a rendition, or artist's rendition of it. Now let me show you ours, which is the actual thing. Now don't forget, they're hitting head on. We're hitting with just into the air with the white particles only. And here it comes. Where is it? Boom. There it is. This is coming through the venturi, and it's hitting here and making all these Higgs fields. And why? What are we looking at? Why is it making these little circles here? Hold on one second. All right, now believe it or not, and this is the absolute truth, all of this was done with a Samsung Galaxy S3 phone from 2012, this phone, using the selfie side, taking a picture of the interaction of the venturi separating the white, and then when it recombines, it makes Higgs fields. They know about the Higgs fields, they just don't know They just see them as a big mess of smashed particles, which I believe I showed you before. This is what they see as this. So they really can't make much of it other than there's different types of particles in here. Some of them take off, never come back. Some of them just sort of hang around. And they assign them energy values, which is true, and they're different colors. The red is the weak, and the blue is the strong. And I could show you the green and the red together and show you how much more powerful the green is than the red. All right, this is the green and the red at the same time through the same venturi. You see the green reconcussing way out here? The red is just pushed out of the way. You see how powerful that green is compared to how dim that looks? The green particles are here. Now, this was not done by Rod Warren. This was done by Fabien Brulé, who was another guy doing some of the experiments with us. And he showed that you can just push that red right out of the way. And you can see the particles tumbling this way. They never ever do that. This one here, because of its energetic, really extremely energetic movement, it just made these tumble. And they normally only spin like this, like that. Now they're going like this. All right, so it just doesn't happen that way. In other words, normally they are spinning just perfectly like this. Now this time they're going, tumbling through the air like that type of thing. That's not the way light is supposed to work. Okay, this is Don Lincoln again. You're talking about the top quark weighing 172.5 billion electron volts. Now, they have found 6 types of quarks. They call them up, down, strange, charm, bottom, and top. And I will show you what I believe they're talking about. Now, up and down quarks make up protons. Up and down quarks make up protons and neutrons. I'll show you that. They weigh 3 million and 5 million electron volts, respectively. In comparison, the top quark, now the top quark, I will show you that one, weighs 57,500 times more than the up quark. The top quark is where all your energy is. Now they say it weighs 57,500 times more. This is where we got a lot of talking to do, because most of the weight is in the muon. Well, virtually all the weight is in the muon, but all the energy, the electron volts, is in the electron neutrino. And when it turns into showers, it turns into extreme amounts of electron volts. Now, he's saying the top quark weighs 57,500 times more than the up quark. Well, the up and down quarks make up protons, and they weigh 3 million and 5 million electron volts. So this must weigh 57,500 times more than 5 million electron volts. So when they say weighs, they mean in electron volts. Now the only thing that has an electron volt in my world is the white particle. So that's where your energy is, but it doesn't have any weight to it to speak of. Right? When they say weighs, that's very, I'd like to talk to him. I would really love to discuss this with Don Lincoln, and unfortunately he doesn't want to talk to me. But anyway, Lincoln offers this, Lincoln offers that. He's the guy that everybody talks to about this. Now he's saying that currently the smallest physical size scientists can measure a particle accelerator 2,000 times smaller than a proton, and that's about right. I have 1,823. All right. So far, scientists have been able to determine that quarks are smaller than that, but not by how much. All right, quarks are even smaller. All right, but they're saying that the smallest physical size scientists can measure, and then they say scientists have been able to determine quarks are smaller than that. but not by how much. So that's another guess. But in order to get it past this, I would have to discuss this with Don Lincoln, because I'm showing the things that they're talking about. And then they're talking about millions of electron volts. And that's okay. Millions are nothing. Millions are tiny. If you can create electron showers, when you create electron showers, you're up into this 57,000 time things. And guess what? These are electron showers. Those are electron showers. And they say that at CERN and Fermilab, we created them. See, this is a whole process. These two are tied together as light, or they're photons. All right, and these are the particles. It's a muon neutrino, electron neutrino. Together they make a Dirac neutrino, or a gluon they call them, which is what was always considered to be an electron. But it has a dark side. Nobody ever knew about the dark side. And that is dark matter as well. So they here and here, back-to-back bar magnets. That's what a photon is. And it's stable. That's why light can bounce and you see it. It's the smallest stable particle. And when you get up bigger than this, they're not stable. And when you get smaller than this, which means just a half of one of these, it's not stable either. It wants to bind with something, but the light particles are stable. They will bounce back at you and you see them as light. Now what we did was putting it through the venturi. It did this. It separated the black from the white. So the muon neutrino and electron neutrino tied together, coming through here as a black and white balls, glued together. They hit here and the white says, I can get through there, but you can't come through, you're too big. And the black says, well, what am I going to do? And it says, well, you're just going to have to go away. And it just keeps slapping the white through. And the white can squish down, as I showed you in this right here. You see how this is getting big puffy? That's because it's hitting these particles in front of it. This one's diminishing because it's behind. It's being shielded by the black particle as the thing goes through the air this way. And this is what it looks like. And and the green is exactly identical to the red, and so is the blue. All right, here's the green right here. And now when they start talking about all these exotic particles, I believe they're talking about these, which are basically neutrinos in the phases of getting energetic enough to become a photon. All right, so they're not really of this magnitude of energy, but they're getting there. All right, and that's why you see them sideways and you see them well, let me show you the red. The red is easier to see. Here's the red. Same stuff. Where is it? Here it is. Okay, here we go. Now, let me turn this off. These are basically going to become photons. So what does that mean? I don't know. All I know is they don't have the energy of a photon yet. A photon, when it gets up to this stage, you're into the full energy of a photon. Normally, I don't think you would see that, except we're going through the venturi and it's stacking back up against all these fields pushing back at it. You see this gigantic field here? That's coming back. And that's why this is so glowy. Normally, I don't think you would see that until it bounced. When it bounced, it becomes the photon, basically. I'm not certain of that, but I can tell you, right, they're all over the place up here. You just can't see them. They're everywhere. And they're just starting to show up here because of the reverse impact of the wave. This one's coming forward and exciting itself because of being dragged forward, so you can see it. And I can show that pretty clearly. Somewhere here. Right here. This one's being dragged forward because of the venturi. And then when it explodes, all of these light up because of the reverse electromagnetic force. You see this wave way out here? You see how powerful that is way back there? And they're all lighting up. All those fields have to light up as this flows back. Now, if we could make that harvest correctly, I don't see why we shouldn't be able to get free energy out of that. It's absolutely no question an increase in luminosity. And luminosity is energy. Just look it up. And it's fully understood. And this is exactly the stuff you want to put in your car batteries. It has no weight to it and has all the energy. All right, if they think light is not going to slow down going through this, all this debris, I mean, that's insanity. It really is. I can't even imagine them saying that with a straight face. These are the fields that are out here. It's absolutely incredible how much resistance is going to be in the way of this light flowing through here. And it's not homogeneous. It's not the same everywhere. So they're just saying that everything's going so fast, pulling away, that the light is shifting to the red by the time it hits us. No, it's just the opposite. Just the opposite. It's just slowing down. All right, it starts out fast like this, and as it comes in, bang, 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 and it keeps slowing down. And by sooner or later, it hits that range where it's no longer moving, and it's just floating around in space, and that creates all that bubbling effect that Don Lincoln calls the quantum foam, where all of a sudden they blink on, blink off, blink on, blink off, all everywhere, because they're interacting with particles coming through. But only for a second, not even just a microsecond. And that creates the haze and the background glow in the universe. You see this? They took the exact opposite of what they should understand from this. Cosmic microwave background is microwave radiation, which is very, very weak. It fills all the space in the observable universe because it's just particles have slowed down. They're just barely moving. It's a remnant, provides important source of data on the primordial universe. They think it all happened at the same time. With a standard optical telescope, the background space between stars and galaxies is almost completely dark. However, a sufficiently sensitive radio telescope detects a faint background glow, and it's almost uniform throughout the whole galaxies and all that stuff. And it is not associated with any star, any galaxy, or any other object. It's just the particles of light that no longer are moving fast. They've hit so many things that they're just barely moving. This glow is strongest in the microwave region of the radio spectrum. Very, very slow. And it was an accidental discovery by an American radio astronomer, Amo Penzias and Robert Wilson. And then they say it's the landmark evidence of the Big Bang theory. No, it has nothing to do with the Big Bang. It's just light that is being emitted from everywhere in the universe. And sooner or later, it slows down till it becomes just nothing hardly. And that's what they're looking at. So that's nothing to do with the Big Bang. Now, how all this stuff got here, I don't know. That I have no explanation for, how it started. And even if God was here, he wouldn't know how it started, because he'd have to say, here's where I came from, and then he'd have to say, well, where'd that guy come from to make you? So you can't get to the back of that. You're just never, ever, ever going to get there. It's just here. From a Big Bang? No, I wouldn't say so, but I can't rule that out 100%. But that is not anything to do with this cosmic microwave background. This is just light slowing down. And as I've shown you, there is no doubt about this, and any rationally thinking person will understand that there is so much dust and fields and light and particles in space, nothing can come through there unaffected. And I showed you light slowing down. I showed you light speeding up. Right? If that's not light speeding up, I don't know what that is light speeding up. Case closed. Nothing else you can say about it. And this is light slowing down. There's no question it's either speeding up or slowing down. It's going fast here, and then it's widening out here. That means it's slowing down. All right, so light can speed up, light can slow down, and the vacuum of space is not a vacuum. It's just like Don Lincoln said. It's not empty. Empty space is not empty. It's completely frothing with these light particles that are out there blinking on and off as they're getting impacted by the light that's coming to us, which is becoming slowed down as well. And sooner or later, that light is going to become part of that background. Okay, so I'm going to sort of wrap this up. This was, again, Don Lincoln about Fermilab. Those are the particles I showed you. Those are the ones we had. This is the quantum foam, which is a dizzying display of change. Empty space isn't empty. It experiences similar activity with subatomic particles winking in and out of existence as they get banged with the light coming through them. This empty space isn't empty. I agree with this completely. And this is about the muons and their spin. And this is about, and again, this is all Don Lincoln stuff. Fermilab, Majorna or Dirac neutrinos, and they're basically Dirac. And this is what CERN is doing, and so is Fermilab. Oh, I'm trying to find out what the smallest building blocks of matter are. Why don't they start with light? Because they're basically the smallest there is. Normal matter is made of molecules, which themselves are made of atoms. Inside the atoms, there are electrons spinning around a nucleus. Actually, no. There's dipole electrons like this, which is the nucleus, and there's a certain number, and at a certain number of stability, it becomes what we would consider an element. All right? It's just more and more. Hydrogen is not one proton or one electron. Hydrogen is something like this. And the core of it is about, let's say, 1823 or 1824. And one more wants to get in, and it says, no, we're stable. We're stable at 1824. We don't want to give one up. We don't want to take one in. We are a stable nucleus. But one more electron wants to get in, and I said, no. So that's when you end up with that quantum effect where there's an extra particle hanging off the edge. When you go to helium, instead of helium having 2 protons, 2 neutrons, and 2 electrons, it has 7,350, something like that, dipoles. All right, so by the time you get up into here, you're up into hundreds of thousands. So this has got to be all changed. Dipole electron flood theory accounts for all of these issues that nobody can account for. They have never been able to find the smallest particle, although they did and didn't realize it. Because this is it. Here they are right here. That's basically the smallest black particle that I know of. And this one here is going to get glowy and not glowy, and they're normally attached together as the Dirac. And I showed you the Dirac, didn't I? Maybe I didn't, but anyway, it's here. Hold on. This is the Dirac. There it is, right there. And again, this was Don Lincoln's article about the Dirac, and that's why I'm sort of chasing after him, because he's the only one who speaks. But he's got a lot of videos. And he says, if you have any questions, ask me. And I tried to communicate with him. I said, Don, I think I found your particles. Can we talk? And he said, no, you don't know what you're doing. And he's refused to make any contact with me at all. And I think we have a chance of actually getting free energy.